Let's get started here. So since we last met, project number 3 was graded and returned to all of you. As I said in my listserv post, the grades were very good, so I don't have any specific comments about the project. Are there any questions from you guys? Okay. Also, project number 4 has been given since our last meeting. We will discuss that project shortly. It is due Friday, March 20th. Are there any questions before we begin? Okay, so we are talking about multinomial regression models in the context of modeling contingency table counts. And basically what we were trying to do was look at how one could, let's say, do a hypothesis test for independence between two variables in a contingency table in much the same way that we did in section 3.2, but now using the information given to us by a multinomial regression model. So just to review, if we have, let's say, x that denotes the row variable and y denotes the column variable, then our model that includes dependence between x and y is shown right here, where we're modeling the log odds, comparing column J to column 1, as a function of our row variable. Since the row variable, of course, will be qualitative, we need to represent in the model by I-1 indicator variables. So if we happen to remove then these indicator variables from our model, then we get the model under independence. So notice since x is not in there at all, that says that these log odds do not vary as a function of the rows. They are exactly the same for every single row. So a test for independence then basically says, okay, let's set these betas corresponding to the regression parameters for the x's, the indicator variables. Let's set all those betas equal to 0. That's our null hypothesis. The alternative hypothesis is, well, at least not all equal, at least some are not equal to 0. Alternatively, we could state this in a, let's say, a full and a reduced kind of model set of hypotheses as well. Then we can use a likelihood ratio test to do the actual test. So that takes us then back to the fiber enriched crackers example. And just to review that for a second here. Let's see here. So there's our contingency table. Notice on the rows we have the fiber variable, which represents no fiber, the bran fiber was used, gum was used, or both. So we have 4 rows. The columns represent the amount of bloating, and this goes from none, low, medium, to high. Notice the zeros that are in the contingency table. This is going to be important shortly. Now, to actually use the multinom function to estimate a multinomial regression model in this setting, we actually have to use a different format of the data. In fact, the format that you use is what we actually read in from the comma delimited file. This is the form of the data that we need to use with the multinom function. So we have a variable called fiber, we have a variable called bloat, and then we have to say, well, how many people were in each of those, essentially those bloat and fiber categories. So that's what the count is doing there. Okay, so let's talk about estimating the model to that data format. So again, I use multinom, formula equal, response bloat, explanatory variable fiber. So again, R is going to create the necessary indicator variables for you. My data is in diet. And then this last part here is what's new to us, a weights argument. This basically says how many observations are in each row of that data frame. And as we saw before, that's what the column count represents. I need that there since I have my data in this structure. Now, an alternative structure that you could have had for your data was, suppose you had 5 rows in your data frame that said gum and high. Suppose you had 2 rows in your data frame that said both high. If you had your data in that alternative format, then you wouldn't have that weight argument that you would need. All that weight argument is telling R is, well, how many actual observations were for that response and explanatory variable pair. It's very easy to forget the weight argument, so please don't forget it. And again, understand that if your data was in this alternative format that I just mentioned, you wouldn't need it. Okay. So I estimate the model, and I put the results into mod.fit.num. Take a look what we have here. It says converged. We'll come back to that. Then we do a summary of what the results are, and this is what we get. So here are all my beta hats that I estimated. Corresponding standard errors are listed there as well. Notice how some of these standard errors are quite large in comparison to the actual beta hats there. We will come back to that shortly too. Okay. So now I want to, given this model's fit, I want to do a likelihood ratio test to determine if bloat is independent of fiber. And so what will be a function to do that? ANOVA, one of the ANOVAs. We're going to use the capital ANOVA that exists in the CAR package. And this is what I get. I get a negative 2 log lambda of 18.9. 9 degrees of freedom, p-value 0.0263. So there's marginal evidence against independence. This is exactly the same negative 2 log lambda, same p-value that we got in section 3.2 when we performed the test using isostats. There we go, right there. Remember that function that was in the VCD package? Exactly the same. Okay. Well, you're both, finding the ratio of two likelihood functions. We're still assuming a multinomial distribution in both settings, so it makes sense that they should be the same. It's just two alternative ways to think about it, from a model point of view and from a non-model point of view, essentially. Okay, so page 345 then. Also, don't forget that you could have used other ways to get this statistic too. Let's make sure you get this. There was a small error in the notes. So this is on 43. I said diet 2. That should be just diet as the data frame. Again, that's on page 43. And there's one more place where I made that error. On page 44, when I refer to the diet data set. Okay, now some comments. So the advantage of approaching it this way instead of what we did in section 3.2 is now we can use odds ratios to better understand the dependence. From just doing a likelihood ratio test or just using the Pearson statistic alone in section 3.2, you don't have that. And this model-based method gives us a direct way to find it. And sure, you could still find some odds ratios by looking at certain 2x2 portions of your contingency table. Yeah, you could have done that in section 3.2. But this model, I think, provides a little bit more of a convenient format to do that. Okay. Since we've done odds ratios already with these kinds of models, I decided not to include that in my notes, but please make sure to take a look at my book that does go through that process. Okay. Now let's talk about these zero cell counts again. These zero cell counts are actually what's causing the large standard errors that I pointed out in the output. Okay? And in fact, if you were to use a more stringent convergence criteria than what was the default for multinom, and if you want to do that, you can use the rel-toll argument that works just like the epsilon argument, essentially, that we saw with the GLM function. If you made the rel-toll smaller, closer to 0, you will see your parameter estimates for this model change. So, therefore, this model actually did not converge. Parameter estimates, I should say, did not converge. Now you might be wondering, well, wait a second. Why are you using this model then to do this likelihood ratio test if you have a model that didn't converge? Well, the reason being is because the actual likelihood ratio test is actually not effective in this situation. Meaning that if you actually try to refit the model and calculate the LRT again with the changed parameter estimates, you'll see the likelihood ratio test for practical purposes does not change, and it will not change. Meaning it will still be what was it? 18.9. Okay.
So we can use the test.
So you could use it in this situation. And the thing is that this will, generally speaking, always happen when you have 0 cell counts. Why? Well, it just goes back to section 1.2 when we were having problems, let's say, estimating odds ratios when we had 0 cell counts. It's the same, essentially the same kind of thing. That you have a 0 in a place that you can't have it to still get an actual estimate. And so that's why that happens. So what can you do instead then, so that you do get convergence? Well, an ad hoc solution is to simply, let's say, add a small number to all the 0 cell counts in your contingency table. So for example, in my book, I demonstrate how to add 0.5 to the cell counts. And then you'll get convergence.
Well, the output says that it converged.
I know.
How would we know that we should not trust?
That's why I pointed out those standard errors. So, and thank you for bringing it up. Whenever you see extremely large standard errors, relative to some estimates, and even some of our estimates were, in comparison to some of the other ones. Remember, everything's measured on the same scale here, because we just got counts. Some of these estimates are kind of large. Okay. I mean, and look at those standard errors too. So whenever you see something like that, that's when you need to start worrying that something's going on. Now, there's been a few times, for example, in this class. No, I won't bring that additional explanation up. Never mind. But that's when you know that you got to start to worry. When you see 0 cell counts and you see stuff like this happening. It doesn't take much to just try to refit the model with a more stringent convergence criteria and see, are your parameter estimates changing or not? If they're not, great, you got convergence. If they are, then you got to worry. Okay, so it doesn't take much to make a check if you see something like this occurring. Okay, so again, make sure you take a look at my book and how I approach this, where I do add the 0.5 to these 0 cells. And that's how you can get convergence. And essentially, it's not going to change your results. Okay. So now, more on a separate topic, although I will relate it to the this fiber example. Now, you can use these multinomial regression models for larger contingency tables. What I mean by that is that, let's say, not only do you have a row variable, a column variable, but let's say maybe you have a strata variable. So a 3-dimensional contingency table. So that might look something like this, where in the fiber example case, suppose we have a type of fiber, and then we have bloat. So here's my contingency tables, let's say. we have these 4x4 contingency tables. We have two of them because they actually represent then basically conditional on a third variable. Let's call it Z, maybe gender. Suppose we have male, and then the second one's female. Okay, so that will be a three-dimensional contingency table. You could estimate a multinomial regression model to this setting too. And this may be one of the possible models that you look at. So again, we're modeling the log odds with respect to the bloating variable. But now, in addition to having indicator variables and corresponding regression parameters for fiber, we also add indicator variables for a third variable. I have, just in general, let's say, suppose you had k levels to your third variable. Obviously, in the example here, I had 2 levels. But you can imagine, or you could have k of those contingency tables for some other kind of version of z. And if you want to test for independence between x and y, given z, well, what would you do?
You run the model with just one
You,
category.
you run the multinom function. Let's say you estimate that, or let's think of it this way. What you're testing is, in that case, are the betas equal to 0 or not in that particular model? So a null hypothesis model would be exactly that model there, except for no x's. That means x is independent of y. You could do a similar thing for z. How about you wanted to interaction between x and z? Suppose how x affects y is dependent upon z. How would you do an interaction in that model? What would you have to add? Excuse me? Multiply each x by z and also have a corresponding parameter to that. So you would have I minus 1 times k minus 1 different interaction terms. And you could have a model that looks like that. You know, then you might want to ask yourself, well, is there an interaction between x and z? Well, how would you test that? Well, set those betas that we just added to the model, set them equal to 0, do a likelihood ratio test essentially. So you can imagine now, let's say if you had another dimension to your contingency table, maybe a 4-dimensional contingency table, you could do the same kind of thing here. Just keep on adding indicator variables. Just a little notational thing here. So notice I have a superscript x there. That doesn't mean I'm taking beta to an x power. Sorry if that was confusing before. It just simply means that these are the betas corresponding to x. Similar thing here. This z there is not taking it to the z power. It's just these betas correspond to z. That's all. Okay. Are there any questions?
So these are tests of independence between fiber and bloating. Can we test that the betas are not equal for all the categories of fiber? Not independence, but that.
So the betas, instead of having all the betas equal to 0, all the betas are equal to one another.
Yeah.
You could do that. Off the top of my head, I cannot think of what exactly that would be testing and why you would want to do that. But it is possible that you could. Just for some reason right now I'm blanking about what that would be. Are there other questions? Okay, so let's talk about the project. Similar format to as before. Okay. So hopefully you remember when I first introduced the fiber data set that I said that you could actually think of that row variable, which represents the fiber type, as essentially two separate variables, meaning either you have added brand or not, so yes or no for brand. You have added gum or not, so yes or no for gum. And so essentially what this means is that you have a 2 factorial experiment here. And the purpose of this project is for you to take a look at the data in that kind of a context, where now you have 2 explanatory variables. And this builds upon pages 168 to page 169 of my book. You'll notice that towards the bottom of my fiber program here, I have some of the stuff that was discussed in the book, such as how to convert the data into this format that we want now to model the data. So this is what it would look like here, where yes, I do. Okay, so the first 2 variables are what we were having before, in addition also, I guess, the count that we had before. And I use some if-else functions to convert the data so that I have brand yes or no, and I have gum yes or no. And so what I like to do is now treat these as separate categorical variables to predict bloating, where here's the number of people that essentially fall into each of those categories. Okay, so you can see there's my if-else function. Take a look at the book. It's explained there. And given that as background, what I want you to do first of all is essentially just run the code that I just did, convert the data to the appropriate format as shown on page 169. So all of you should get this problem right. Okay? Then part B, with the multinomial regression setting, what I want you to do is estimate the model that has brand and gum only, no interaction. My book talks about interactions. With no interaction, using the default model convergence criteria that would be multinomial. So essentially how we've been fitting the models, these kinds of models so far. So don't use that rel-toll argument that I had briefly mentioned. Okay. Then the next part says, show that convergence of the parameter estimates was not actually obtained. So, just like what we saw, R was saying you have converged, when in fact you haven't. So that's where you can use the rel-toll argument, try a stringent model convergence criteria than what's in the default. You have to probably look at the help for multinom to figure that out. Refit the model, and you will see the parameter estimates will change. Next, add 0.5 to the cell counts in the data, similar to what was done on page 166 of my book. Re-estimate the model and show that convergence does indeed occur. Now, you can't just, again, rely on R saying converged, as we saw. So what would you do? Well, try to re-estimate the model with a more stringent model convergence criteria and look to see with the normal criteria versus the more stringent, are my parameter estimates changing or not? If they're not changing, okay, that must have meant that you did have convergence before. Then lastly here, use odds ratios. I don't know why I needed to capitalize the U there, but maybe I was just trying to emphasize it. Use odds ratios to interpret the effect of brand and gum unloading with this model that we've just been looking at that has no interaction terms in it. Okay. So that's part B. Part C, you're going to do some similar things using the what's called a proportional odds regression model, and that's the subject of our next set of stuff in the notes. Part D, you're going to make some comparisons between the two models, multinomial and proportional odds. And then lastly, number 2 here, you're going to just simply derive some odds ratios corresponding to a general multinomial model, not in the context of the fiber data. Okay? I don't think that this project will be too difficult. Hopefully grades will be as good as they were last time. Are there any questions? Okay. So we are now on page 47 of the notes. So we will still have a multi-category response, which we will call Y. The difference now is that the response itself, the categories, have some kind of ordering to them. So in some way, category 1 is going to be less than category 2. It's going to be less than category 3, all the way up to category J. One common place where this occurs is, for example, when you take maybe some kind of survey, you've probably encountered Likert scale responses, from strongly disagree, disagree, neutral, agree, strongly agree. Those 5 categories have an ordering to them. With the fiber data, the bloat variable has an ordering to them. None, low, medium, and high for the different responses. Okay. So if you have that kind of ordering to it, so far everything that we've been doing is just ignoring it. So essentially we're ignoring potentially useful information. So when you have this ordering, most generally you want to take advantage of it. And so you want a model that takes into account that ordering. And what you'll see here, especially with the fiber data, once you do that, your conclusions change. And you find out some stuff about the fiber data that we might have missed before. Okay, so now there are a number of different kinds of models that can take into account this ordering here. We will talk about what's the most common, which is called a proportional odds regression model. And this proportional odds regression model models cumulative probabilities. So we've seen cumulative probabilities before. We're going to be modeling, in our case here, the probability Y is less than or equal to our category J. And the way that we do that is going to be somewhat familiar based upon what we did in Chapter 2. We are going to look at the logit of the cumulative probability. In other words, the log of the probability that Y is less than or equal to J divided by 1 minus the probability Y is less than or equal to J. So what is this right here that I'm circling? What's another word that we've used for that? It's an odds. But it's an odds involving cumulative probabilities. So in other words, we're looking at the odds that you are less than or equal to category J versus you are greater than category J. That's what we're going to be modeling now. I think it's kind of interesting to approach this in this kind of a framework. We want to see, then, if these log odds change as a function of an explanatory variable. So let's say that we have one explanatory variable, we'll call it x. And this is what our model is going to look like. And I'm just going to write this out here just for emphasis to remind you what we're modeling. Perhaps I don't need to. So, does this log odds vary as a function of x? So just like what we did with the multinomial regression model, we have this intercept term, which is beta j0. So notice that we have that j in there, so that we have these regression parameters changing as essentially, or we have a different one for each, almost for every column. But look at this here. We just have a beta 1. We don't have a j there, unlike what we have with the multinomial regression model. Notice what J is between 1 and capital J minus 1. You might be wondering, why don't we go all the way up to capital J? Have the answer there? At least I don't see it off the top of my head, or I don't see it from looking at it immediately. Why don't we go all the way up to capital J? Why do I have a minus 1 there?
Some of the probabilities add up to 1.
Yeah, all the probabilities are going to add up to 1. So the probability y is less or equal to capital J is 1. So that's why we don't include it. We know what that probability is. It's going to be the same for every single problem, every single data set. Okay? We could rewrite this model in the following format, similar to what we did with logistic regression. So all I did was I had that log on that left-hand side. I just raised both the left-hand side and right-hand side to use the exponential function with it. And so now you can see the odds are equal to e raised to the beta j0 plus beta 1x. I could also rewrite then the right-hand side of the model such as this, or like this. Right? Okay. Now notice no matter what j I have in there, j equal 1, 2, all the way up to capital J minus 1, that area, that portion that I just highlighted does not change. So you can see that this odds is essentially proportional. So, in a mathematical context, if I write out y is equal to x times k, we say that x is proportional to y if k is constant. Well, notice here's my constant. No matter what j is, I have the same. So that's why it's called proportional odds regression model. We could go a few more steps further, just like what we did with logistic regression, and you could have an expression, you can find an expression for the cumulative probability just in terms of our, essentially our betas. That should look familiar from chapter 2. Okay. Now, with this form of a model then, I'll make sure you make that change there. That should be, I think I left off the j, I left off a minus 1 in the subscript. Okay. Now, since we're working with cumulative probabilities here, and things are not, excuse me. Since we're working with cumulative probabilities here, we have this ordering amongst our intercepts. Because as j is increasing, this cumulative probability has to increase as well. And so because of that, we have this ordering amongst our intercepts. Also, this proportional odds model is actually a special case of simply cumulative probability models. There's a number of different cumulative probability models out there. This is the most used one, so that's why we are discussing it here. But there are other models, and we will briefly see one of these that allow you to have actually a subscript on that j there. Now you might be thinking, well, yeah, I want that freedom. I want to be able to put a subscript j there. what you will see later is that you may not actually want to have a subscript j there. By us actually not putting a subscript j there, it helps us to better account for this ordering that we have amongst these categories there. Because again, this is staying constant as you go from category j equal 1, 2, 3, and so on. Once we see some plots, I think it will be clear if it's not already. Okay. So we could have, p different explanatory variables. So that's what a proportional odds regression model looks like with p explanatory variables. Again, notice that when you're stating the model itself, you're going to have p different betas, and then you also will have j minus 1 of these beta j zeros that you have to account for. Well, what about, given this model structure then, well, what is just pi sub j itself? Again, what is that probability y is equal to j? So with a multinomial regression model, if you remember, we went through like a little proof that showed what pi sub j was. Well, we're going to do the same thing here. So to find this, just write out what probability y is equal to j. Write it in terms of cumulative probabilities. That's the trick, if you want to call it that. So I'm going to write it in terms of the probability y is less or equal to j minus the probability y is less or equal to j minus 1. Because, when you subtract that portion on the right-hand side, well, what you're left with, well, just j itself. Well, remember, that's what we're essentially modeling here. So here's my model. It's written just like that. So I substitute that model then into this portion right here. And I'm just writing in terms of 1x because it's just a little bit easier. This works, what I just showed you, for j equal 2 to capital J minus 1. It works for j equal 1 and j equal to capital J, but you have to be careful. Okay, first of all, let's see, what was the problem with that? Yeah, I forgot the 1 subscript on that beta. So let's look at little j equal to 1. In other words, what is pi sub 1 itself? Well, probability y is equal to 1. Okay. Well, since I'm not going to have a category 0, I'm not going to have a category minus 1, and so on, that means that this is equal to, well, the cumulative probability. Probability y is less than or equal to 1. And you just get that directly from your model. How about for the capital J category? So I want pi sub capital J. Well, that's equal to probability y is less or equal to j, capital J, minus probability y is less or equal to capital J minus 1. All I'm doing is doing exactly what we had up there. But what is this probability y is less or equal to capital J? 1. And then you can find the probability y is less or equal to capital J minus 1 rather simply, and that's what you get. So that's what your pi's are. On a test, I've actually asked for students to derive for me, what is pi sub j in the context of a proportional odds regression model. That's all you do. Any questions?
Can we go through it again?
Excuse me?
Can we go through it again?
Sure. We do some erasing. Okay. So, what is the probability y is equal to j? In your very first stat course, when you first talked about discrete random variables, let's say you had a random variable x. Well, how about we put it in this context? No, I don't want to do that. Let's say, again, you have a discrete random variable, x. And you wanted to find, well, what's the probability x is equal to 5? And so one way that you could do that is to say probability x is less or equal to 5 minus the probability x is less or equal to 4. Where I'm assuming that, being discrete, meaning that it can only take on integer values okay? And so that's essentially what I just did right there. And now to get these terms, I just go to what my model gave me on page 48. Does that make sense so far? Okay.
Mm-hmm.
Now, what if you want then just for the first category itself? Well, it would be probability y is less or equal to 1 minus the probability y is less or equal to 0. Well, since I don't have a category 0, that means that this probability is 0. And so I'm just left with probability y is less or equal to 1. And again, I get that directly from my model. Then lastly, for the probability y is equal to capital J, I again do that little subtraction once again. And then, as you mentioned earlier, this probability has to be equal to 1. Because they're only capital J categories, so you have to be in one of those categories. And then again, I just go to my model itself to get the other expression. Does that help?
So does the negative after the 1, what happens to that negative? 1 minus?
Well, that negative, let me do some erasing. Oops. Where's that negative coming from? Right here. Right here. That's where the negative is coming from. It's the subtraction that we saw earlier. So let's take a look at some plots of this model. I think it's always nice to be able to look at a picture to see it. So let's say that this is my model here. I have just one explanatory variable again. Its beta is going to be set equal to 1. So beta 1 is equal to, I'm sorry, it's not going to be set equal to 1, it's going to be set equal to 2. Beta 1 is equal to 2. And I'm going to have 4 categories in total. And I'm going to have to then set 3 betas. Beta 1, 0, beta 2, 0, beta 3, 0. Notice how these are equally spaced. I didn't have to do that. I just wanted to do that because I think it makes the plot look nice. But also notice how they are increasing. Because again, these cumulative probabilities, as j goes from 1, 2, 3, those cumulative probabilities are going up, 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 up. And if you actually going to take a look at what your model's shown you, for fixed x, let's say, in order to go from, let's say, category 1 to category 2, I need this probability to be bigger. So what's the only thing that I can do? Increase this beta. Go from category 2 to category 3. What's the only thing I can do? Increase this beta some more. That's going to make this cumulative probability increase. Okay, so this is what the model looks like when I graph it. So let's take a look on the left-hand side there. I have cumulative probabilities on the y-axis. On the x-axis, I have values of x. And so we can see for the probability y is less or equal to 1, it's my black line, I get a curve that looks very similar to what we saw with logistic regression. Well, that should make sense, because again, we have this e raised to some power divided by 1 plus e raised to some power. That's why. Now, when I increase my intercept from 0 to 2, then that should mean to you, okay, I'm going to get higher faster in terms of x. So now, look what happens. The red dashed line represents then probability y is less or equal to 2. And again, that's when, I'm getting really messy here. When y is less or equal to 2, that means I have a beta 2, 0 in my model, and beta 2, 0 is equal to 2. And so we can see that we have exactly the same shape as what we did when we were looking at probability y is less or equal to 1. Exactly the same shape. Because again, that beta 1 times x is fixed. I guess the x is varying here. I shouldn't say that. But that beta 1 stays the same for whether you're at j equal 1 or j equal 2. That's why you have exactly the same shape. So this, this shift that we see in that line there is corresponding to that beta 2 is equal to 2. And then if I increase my intercept by 2 again, look at how I have exactly, it looks like the exact same shift. I have the exact same, essentially the same kind of line there, just shifted a little bit. Are there any questions? Let's look at the plot. Let's look at the plot on the right then. So now on the y-axis, I have pi sub j. Sorry, that's small. So just the probability y is equal to j itself. And you can see for the case of pi 1, in terms of x, in terms of that x-axis there, it's going to take longer for, or it's going to take, I shouldn't say it that way. Excuse me. We can see for high values of x, that's when it's going to start to get to its maximum point. For pi 4, notice that it reaches its maximum point for smaller values of x. And then in between here, we have the maximum point for pi 3 and also pi 4. So if you were to, let's say, maybe think of this plot in terms of trying to use this for classification. You know, let's say I want to use this model to classify observations in category 1, 2, 3, or 4. What we see here is that there are particular regions as a function of x that you would use to make a judgment of, well, should I classify this in category 1, 2, 3, or 4 in terms of which probability is the highest. So for example, for low values of x1, the highest probability corresponds to category 4. So you would classify that observation in category 4 if that was the purpose of what you were doing. Okay. Now this program, take a look at my program. You know, how did I do these plots? What function do you think I used? Well, I guess I have it right here, the curve function. Okay. Take a look at my program. You know, we've done these kinds of plots before with the curve function. That's why I'm not presenting the code here again. But what you can do is play around with the different values of beta and see how it changes the plot. And that will give you a better feel for what this model is doing. Are there any questions? Okay, so how do I estimate these models? No, maximum likelihood estimation. Remember, I think it was page 3.3 of the notes where we wrote out a product of m different multinomial distributions, and that was our likelihood function. Well, essentially, all you do to come up with the maximum likelihood estimates for the betas is you plug in the values of pi that we have, as I was demonstrating before. There we go. So, oops, there we go. So here's my pi sub j, written in terms of my model. You plug those into your likelihood function wherever you see a pi. Now your likelihood function is a function of the betas. Maximize that likelihood function, find the betas and maximize that likelihood function, given your data. Use numerical iterative methods to do that, and that's how you get your maximum likelihood estimates. Just like what we did with the multinomial regression model. The function R that will do this automatically for us is called POLR. Stands for proportional odds logistic regression. So you just stick an L in there because we're essentially using that, as we saw in chapter 2, that transformation that comes about through using from the cumulative distribution function of a logistic distribution. And we're not assuming anything has a logistic distribution. It's just we're using that mathematical form. You could use other mathematical forms as well, but we're just going to use the one that we've been talking about. This function is in the MASS package. MASS stands for Modern Applied Statistics with S, which is actually the title of a quite famous book on using S, S+, and R. And so it's actually a package that, it's a package that comes with the book. Since the package is used so much and the book is so famous, the package is actually automatically installed in R. So by default. So you don't need to actually download it yourself, but anytime that you want to use functions from this package, say library maths, just like what we do with the NNET package. Now you have to be very careful when you estimate these models with POLR for a number of different reasons. First of all, since our response variable has that ordering to it, you need to make sure that R recognizes that ordering. So you'll see an example coming up shortly. So you need to make sure that R recognizes that the first level, let's say for the fiber bloating variable, is none. Next one is low. Next one's medium. Next one is high. And R needs to recognize that. You can use the factor function to get that done. The covariance function for the parameter estimates comes about through the same kinds of methods that we talked about before. Minus the expected value of the second derivative of log likelihood functions evaluated at the parameter estimates. Take the inverse of that matrix. You can use walled and likelihood ratio based methods just like what we've done before. Okay, so this takes us to page 52. Now one thing that you have to make sure you do understand when you are doing, let's say, hypothesis tests or even some other stuff with this model is you have to be careful about, well, what does this exactly mean when you do a hypothesis test like this? So, let's say you have a proportional odds regression model. You're testing one parameter, beta 1. So if beta 1 is equal to 0, what does that mean? Well, it means then that X is not in your model. Okay, we saw that with the multinomial regression model. So nothing new there. What's new is, well, what does then the alternative hypothesis mean? So let's look at the model itself. Okay. Now what this is saying is that you have this particular ordering amongst your categories. This model does. So it's not necessarily exactly the same as what we saw with the multinomial regression model, which I think I have down here when we were testing similar hypotheses. In that case, if I were to focus on the betas corresponding to X, note that I would have more than one beta. But if the alternative hypothesis was true, I wasn't necessarily saying anything about any kind of ordering amongst my probabilities, which I am with my proportional odds model. That can be both a strength and also, depending upon the application, maybe a weakness of this approach. You'll see that especially when we do the fiber example. Okay, so let's take a look first at the wheat example. So we have three categories for these wheat kernels: healthy, scab, and sprout. All of you should agree with me that healthy is the most desirable. Okay, so how about we make that the last category? So then we need to say, okay, well, is there an ordering between sprout and scab? If there is, and that says, hey, proportional odds regression might be an approach here that we could use. Because now we have, for all the three categories, we have a particular ordering. Well, I think it's not necessarily clear that there is an ordering, but I think it's reasonable. Again, this is more my judgment here, not necessarily the judgment of the grain scientists. I think it's reasonable to say that scab will be less preferable to sprout, because scab represents a diseased kernel. Maybe you might not even want to use it. Where if something's sprouted, well, you might still get some use out of it. So because of that, I'm going to use this kind of an ordering: scab, sprout, and healthy. Now again, it is somewhat debatable if this is really what a grain scientist would do, but the reason why I like to use this is because it allows us to make a more direct comparison between a proportional odds model for this data and then also a multinomial regression model for this data that we had last time. That's why I like to use the same data set. Okay, so the first thing that we need to do is look at, well, what is the ordering that R sees our response variable with right now? If you remember, our response variable is in the type variable of the wheat data frame. So use the levels function. Notice that it actually puts healthy first. We want healthy to be last. That's our last category. So when we do that ordering, healthy is the best. So what we can do then to make that change, there's a few different ways to do it. We're going to use the most general way. We're going to use the factor function. So we say factor, then the variable I'm interested, type, and then I'm going to put new levels in, a new ordering for the three levels: scab, sprout, and healthy. I'm going to put that back into the wheat data set in a brand new variable called type.order. So I can quickly create that new variable in the data set using this kind of a syntax. And now when I use the levels function with type.order, I get the correct order. Note that my response variable itself is not changing at all. So the first observation of the data set is actually still healthy. It's just how R recognizes the orderings of the levels that changes. Is there a question?
I'm assuming that R uses the same level differences for each of the orderings. Like the difference between scab and sprout is maybe one level, and between sprout and healthy is another one.
Yeah. So in here in this categorical setting, we don't necessarily say, I'll just make something up here. Suppose scab has a level of 1. And let's think of it as a numerical number. Maybe sprout is 3, and healthy is 10. So notice that those are not the same. The same distance, or this is saying to let's say maybe that healthy is much more preferred. We're not talking about those kinds of models. Okay. Okay. So this is the model that I would like to estimate then. If you remember, we had 6 explanatory variables. X1 was the class of the variable of the wheat. Was it soft red winter wheat or hard red winter wheat? X6 was actually I think it was the moisture content of the wheat. So to estimate the model, I'm going to first make sure that R knows I want to use the PLR function in mass. So I say library mass. So now I can use the PLR function. And just like what we've done with other functions, I say formula equal, I put my response, type.order, tilde, and then I just put in my explanatory variables. My data is in wheat, and this is the default, so you don't need this, but I put this for emphasis, method equal logistics, so that we get the same kind of transformation the exact same transformation that we were seeing before. You could use probit there, actually, too. You could use complementary log-log, too. I don't think it was really worth our time to go into that. Just a different form of this kind of a model. Again, generally speaking, most people will use this logistic transformation, essentially. So then I put the results into mod.fit.org, and I summarize the information that the model gives me. and this is the output. We've seen output like this before, just for a different model. But the thing that you have to be careful about here are these estimates. So you might be thinking, okay, those are my beta hats. So you might think that this one right here is actually beta hat 1. Actually, it's not exactly. Instead, it is the negative of beta hat 1. This here is the negative of beta hat 6. Here, this is beta hat 1, 0. This is beta hat 2, 0. So what R is actually estimating is a slightly different model than what we had introduced. It's actually estimating this model, where notice we have negative values in front of the coefficients, these parameters of our x's. So eta 1 hat, so eta 1 hat is 0.17. Beta 1 hat is negative 0.17. Why this function estimates a model like this? I've never seen it with any other kind of model do this before in any other statistical software package. Why it estimates with a negative out there? I don't know, but that's what it does. You can obviously see, though, if you don't pay attention to that, your interpretation can be exactly opposite of what it should be, essentially. So be careful about that.
Oh, sorry, what is beta again? What is the eta?
Right here. So this is the model that it's estimating, with negative signs out in front of your, the multiplication of your regression parameter and the explanatory variable. That's what it's trying to estimate. Where every other kind of model we've had, and every other model that I know of, we'll put a plus there instead.
So we haven't encountered the eta time up until now.
This was the first time that I introduced you to the eta, yes.
Okay.
Obviously, on a test situation, if you're not paying attention, you can make an error here. Often in test situations, I shouldn't say often, but sometimes in test situations, I will have students think, oh, I need a negative out in front of 17. No, you don't. It's only for the regression parameters that are coefficients on the x's, not the intercepts. The intercepts are fine.
Can I ask a question?
Sure.
Why don't you have this graph to help with that?
Say that again, please.
Why in intercept you only have scrap and sprout and healthy?
Okay, yeah. Sorry, I didn't explain that very well. So, look at what your model is here. Let's see. I'm going to write it out like this. Okay, so this is the beta hat corresponding to when you're at category 1 and everything less than 1, and then essentially category 2 and everything above. So what the log odds are here, notice how I rewrote it, so it's probability y is less than or equal to 1 divided by probability y is greater than or equal to 2. So scab is 1, sprout is 2, healthy is 3. So that essentially, I know it's not necessarily completely obvious, but that's where that's coming from there. So the 1 and then the 2. That's why it's telling you that.
Sometimes
What?
Is it the same thing that some people call it threshold?
Threshold? You could kind of maybe say that. I wouldn't say it in this context. I haven't necessarily seen anybody say it in this context either. But I guess a 1 is a threshold. Are there other questions? So this is what the actual estimated model looks like then in terms of our notation. So again, notice these negative signs there. Compare that to the output. Also notice how you state the estimated model. Notice the hat on top of that P there. You need to have a hat there because now we're talking about estimated cumulative probabilities rather than the true cumulative probabilities. If you don't have the hat there on a project or a test, I will take off points every single time. Please don't let that happen to you. I don't like doing that. Also notice how I state the model where I have just simply beta hat J0 in there in my equation, and then later I define what those beta hats are. Otherwise, what I would have to do is write out essentially 2 different lines or 2 different equations, and this is just easier. So it's the only thing that's changing between what will be 2 equations is this beta hat J0. Now if we go back to the output again, so we have these standard errors here. Okay, well what are those? Well, it's the square root, the estimated variance of beta hat 1. Why is it negative beta hat 1? Well, it is. Also. Why is that? Come on, stat majors. Tell me why it's exactly the same. Let me make sure that that's clear what I said. So the square root of the variance hat of beta hat 1 is exactly the same as the square root of the estimated variance of beta hat 1 with a negative out there. Sorry, there was a bunch of people now who said stuff. We'll go over here first.
Square.
Yeah, the square. So when I factor this out, and of course that's equal to 1. That's why. Okay? Well, I have really made a mess here. Now, this T here, what do you think that is for? It's a test statistic, a walled statistic that's testing gamma 1. Oops.
Beta?
I'm going to do gamma first. Gamma 1 is equal to 0 versus gamma 1 does not equal 0. Okay? This is also testing the betas too. But if I want to do a hypothesis test for the betas, so here's my, let's say my z test statistic is 0.44, just take the estimate divided by the standard error. If I want to do this hypothesis test, what's my z? Give me a numerical value. Is it 0.44?
0.44 square.
No, negative 0.44. Okay. Now in the end, this is probably not a big deal because we know walled tests are probably not going to be as good, or I shouldn't say probably, are not as good as likelihood ratio tests. So we're going to be using likelihood ratio tests. So again, we could use the CAR package, use the capital NOVA function, and do our likelihood ratio tests. So for example, let's take a look at density. My negative 2 log lambda statistic is 98.4. What this is testing is, given all the other variables in the model, let's just look at density itself. Is density important? Yes. Very large negative 2 log lambda. My p-value is extremely small. Similarly, weight has a very small p-value at all as well, and hardness has a marginally significant p-value. Again, these are conditional on all the other variables remaining in your model. It's testing your corresponding parameter for a particular variable. So, you can do likelihood ratio tests. Please note, though, unfortunately, profile likelihood ratio intervals for various things are not as easy to find. The MC profile package does not work here. It's unfortunate. What about if you want estimates of your pies? So the probability that you have a scab, probability you have a healthy, probability you have a sprout. How can you do that? Well, as you might expect, use the predict function. So I say predict. Here is my object that contains my model fit information. And then I have one argument called prob or type, where I use probs as the argument value, which says I want probabilities. I put that in an object called pi.hat.org, and this is what I get. So if we look at the very first observation, we can see that pi hat 3, which would correspond to healthy, is 0.69. Pi hat 1 for scab is 0.036. For sprout, pi hat 2 is 0.273. So if I wanted to use this information and to predict a classification for the first observation, what would you predict? Healthy, because that's the largest probability. If you want to do that more automatically, you could use the type argument equal to class for classification, and you can see the very first observation is classified as healthy.
So is that necessary that pi hat 2 is lesser than pi hat 3?
Well, for this first observation, that's what ends up happening. And if you were to do a classification, you take then the, makes sense that you would take then the probability that's the highest, the corresponding response.
0, 5, the pi hat 3 does not lesser than pi hat 3.
Yes, so that was sprout. So the fifth observation has the highest probability would be for sprout, not healthy in that case. And so that's why you have that classification. Now, of course, I do expect you to be able to do these calculations, let's say, by hand. And so I just threw out a pi hat healthy there, just to show you that indeed it's not that difficult. You just have to write everything out, and you get exactly the same answer. What about confidence intervals? Well, we run into the same issues that we had with the multinomial regression models, where what we like is actually it's a confidence region, and we don't have an easy way of doing that. You can still do one at a time confidence intervals, with the caveat, of course, that you may actually end up having some of the probabilities. If you look at all the categories, some of the probabilities being greater than 1, which obviously is not good, but I guess it's better than nothing. In my program, I show you how you can do that. I'm not going to ask you a question on a test, though, for how to do it. And lastly, let's take a look at the situation where, let's say that we just have density in our model and we re-estimate the model. We did this with the multinomial regression model too. And this is what we get. And let's do a plot of our estimated model in. Fortunately, my mouse is not working. There we go. And so what we have here, the thicker lines is from our proportional odds regression model. The thinner lines are from our multinomial regression model. And so on the y-axis, we have the estimated probability of being in a particular category. On the x-axis, we have density. And that's why I chose to have a model that only had density. And what we see for the two different models is something very similar. And so, while I was, questioning earlier if my logic behind ordering a sprout, scab, sprout, healthy is actually true, perhaps kind of it reassures me a little bit that when I compare the two different models here and looking at their estimated probabilities for each category, I get something very similar. Okay. Are there any questions? That clock's fast. I am ending right on time. If there's no questions, then we will stop.